Let's dive right into one of the biggest, most mind-bending questions in all of science. We all walk around in this world that feels pretty solid, right? A chair is either here or it's not. But the quantum mechanics that governs everything paints a totally different picture, one of a fuzzy probabilistic haze. So how do we get from that quantum weirdness to the concrete reality we see every day? What is really going on when we're not looking? Really think about that for a second. Quantum theory says a particle, like an electron, it doesn't have a definite position until we measure it. So what is it before that? Is it everywhere at once? Nowhere at all? This one question just shatters our most basic ideas about how the world is supposed to work. And this gets us right to what physicists call the ontology problem, which honestly is just a fancy way of asking, what does quantum mechanics say is actually out there? What really exists? And this is where things get really, really different from the world we think we know. Classical physics, Newton's physics, it's comforting. It tells you exactly where Mars is in its orbit. But quantum physics, it's a totally different story. It doesn't tell you where an electron is, it just gives you the odds of where you might find it if you decide to look. It's like, at the very bottom, reality is just a game of chance. This whole probabilistic thing is so strange that, as physicist Jean Bricmont points out, it forces scientists into using language that sounds way more like philosophy. If something only gets a definite property when it's perceived, well, it makes you wonder, right? Is anything real when nobody's looking? That's the problem. And of course, this leads us to the ultimate, famous, kind of creepy thought experiment, Schrödinger's cat. You link a cat's life to a random quantum event inside a box. The theory says until you open that box, the cat isn't alive and it isn't dead. It's in a superposition of both states at the very same time. How on earth can a cat be both alive and dead? Okay, so there's a really obvious common sense pushback to all this weirdness. But as we're about to see, reality is even stranger than it looks, and the biggest clue is hiding in plain sight. It's the environment itself. So here's the idea that feels right, what they call the ignorance interpretation. Maybe that electron does have a real position the whole time, and we're just ignorant of it. Like a coin I've just flipped that's now hidden under my hand. It's already heads or tails, I just don't know which one yet. Seems logical, right? Nope, wrong. And this is a huge deal. Physicists proved that this simple, common sense idea of hidden variables just flat out doesn't work. It's not an opinion, it's a mathematical fact. These no hidden variable theorems show that if you assume particles have pre-existing properties, you end up with conclusions that contradict what we see in experiments. So the easy answer is off the table. The mystery is a whole lot deeper. So if that's not what's going on, then what is? Well, this is where the hero of our story comes in, a process called decoherence. And the key idea is this: nothing is ever truly alone. There's this constant, relentless interaction between any quantum system and its environment. We're talking air molecules, stray photons, you name it. Everything is constantly bumping into everything else. You can almost think of it like the environment is constantly watching. Now, it's not a conscious observer, of course, but through countless tiny little interactions, it's effectively measuring the system over and over again, leaving a tiny record of its state scattered all around it. No system is ever truly isolated from this. Okay, so this brings us to the big breakthrough. What does all of this environmental monitoring actually do? Well, it solves the most immediate part of the paradox, why we never see things like a cat being both alive and dead at the same time. So to get this, you have to know a little about something called interference. In a perfectly isolated system, the quantum waves that describe a particle can overlap and interact with each other. This is what's behind all the quantum weirdness, like an electron magically going through two slits at once. And yeah, if you pull this off in a lab with a totally isolated system, you get these beautiful, ghostly interference patterns. It's the smoking gun, the clear proof of quantum superposition happening right in front of you. And this is everything. The second that system interacts with its environment, decoherence kicks in. All those tiny, constant interactions, they just scramble the delicate relationship between the different parts of the wave. And just like that, the interference and all the obvious quantum weirdness just vanishes. So how fast does this happen? Is it a slow fade? Not even close. For a tiny speck of dust is floating in the air, the time it takes for decoherence to wipe out its quantum properties is about a nanosecond. It is one of the fastest, most ruthlessly efficient processes in all of nature. It's basically instantaneous. So here's the punchline.
the world starts to behave as if a measurement had already been made. Decoherence doesn't actually destroy the other possibilities, but it makes them stop interfering with each other. The system now just looks like a normal, classical mix of possibilities, not some weird quantum smear of them.
Okay, let's go back to our cat. The alive cat state interacts with the air in the box totally differently than the dead cat state. Decoherence kicks in like lightning and forces these two possibilities onto completely separate tracks. They become separate, non-interfering branches. That's why we never ever see a blurry half-alive, half-dead cat. The environment has already forced a choice between classical-looking options.
But, and you knew there had to be a but, right? Decoherence is a massive, massive piece of the puzzle, but it is not the final answer. It doesn't solve everything. What it does is set the stage for the final, and maybe the deepest mystery of all.
See, here's the catch. Decoherence is brilliant at explaining why the world splits into these clean, classical-looking branches, why the cat is either alive or dead, but not both at once. But what it doesn't do is pick a winner. It doesn't tell us why when we open the box, we see an alive cat instead of a dead one. It creates the menu of possible realities, but it doesn't place the order. And this is exactly where all those different interpretations of quantum mechanics you've heard about come back in. They all need decoherence to even get started. For a many-worlds person, decoherence is the engine that creates all the branching worlds, and they say all of them are real. For a pilot wave theorist, it creates the different channels that a particle can get locked into. For a collapse theorist, it provides the nice, neat, classical options for the wave function to collapse onto. It prepares the stage for the final act of the play.
Which leaves us with this final, absolutely mind-blowing question. Decoherence shows us that with every single quantum interaction, the universe is constantly branching into countless parallel, classical-looking realities. If that's what's happening, it means that right now there are other versions of you experiencing every other possible outcome. So, which one are you in? And why this one? And that's the edge of what we know, and the incredible mystery that's still waiting to be solved.